All right, so we're going to see how we can use trig identities to help us solve certain trigonometric equations. This is the last lesson of this chapter. You guys are going to have a quiz on Tuesday, and then I will also hand out the review assignment on Tuesday for you to start working on because your trig exam will be on Thursday. That'll cover chapters 4, 5, and 6. So I actually have the review now, so I can give it to you after the lesson, so you can start working on it over the weekend. You're gonna have to go back and look and remember how to do the stuff from chapters 4 and 5. This is how we separate the men from the boys. What? Okay, so we're going to look at solving trig equations algebraically using known identities, determine exact solutions for trig equations where possible. We'll do some general solutions for trig equations, and then also identifying correct errors in a solution for a trig equation. So to solve some trig equations, we need to make substitutions using the trig identities that we have studied in this chapter. This often involves ensuring that the equation is expressed in terms of one trig function. So you either want to have all cosine or all sine, and we'll see examples of when that needs to be done and how we do it. So this says solve each equation algebraically, and notice the domain. And that's really important that you look at what the domain is, because it tells you where you're going to look for your answers, but also tells you whether they need to be in degrees or radians. So this domain says that x is greater than or equal to 0, but only less than 2 pi. So you want to have all answers between 0 and 2 pi. 0 could be stated as a solution, but 2 pi wouldn't be, because it says x is less than 2 pi. Also, our answers have to be in radians, not degrees. So for the first one, we have cos 2x plus 1 minus cos x equals 0. So remember, we have three different options for cos 2x. There's cos squared x minus sine squared x, 2 cos squared x minus 1, or 1 minus 2 sine squared x. Because we have a term here of just cosine x, I'm going to use the substitution for cos 2x that only involves cosine. I'm going to use the fact that cos 2x can be written as 2 cos squared x minus 1. It only involves cosine. Now, it's true there is another term there, the 1, but that's fine. We just wouldn't want any terms involving sine. The rest of the equation, remember, this was just a substitution for cos 2x. Then there's a plus 1, and then there's a minus cos x equals 0. And when you simplify this, the minus 1 plus 1 cancels. So we're left with 2 cos squared x minus cos x equals 0. So now we're going to solve this equation. This is a quadratic because there's a cos squared x and a cosine x. And normally we solve quadratics by factoring. And in this case, there is a common factor of cosine x that we can take out. So common factor of cosine x taken out leaves us with that. And our solutions will come where each factor equals 0. It's where the cosine of x equals 0 and where 2 cosine x minus 1 equals 0. Or where the cosine of x equals 1/2. If you add 1 and divide by 2, that's what you'll get. I'm just going to open up a unit circle here. There we go. So our solutions were cosine of x equals 0. So once that unit circle opens up, we'll be able to see where that is. The cosine, remember, is the x value. again. There we go. And that is 0 up here at pi on 2 radians and down there at 3 pi on 2. Remember, the domain tells us our answers have to be in radians. So there's our first two answers, pi on 2 and 3 pi on 2. And our second set of solutions will come where the cosine of x equals 1/2. And remember that cosine is the x value, and that equals 1/2 here at pi on 3, and down here at 5 pi on 3. So there's our other two answers, pi on 3 and 5 pi on 3. And once you find these solutions, you can always check them in your calculator. So in this case here, we have to make sure that we are in radian mode because our angles are going to be in radians. And first I'm going to check pi on 2. So cosine of 2 times pi on 2, I'm going to put the pi on 2 in brackets just to make sure it's kept together as a rational number. So there's the cosine of 2 times pi on 2 plus 1 minus the cosine of pi on 2. According to the equation, that should all equal 0, and it does. So pi on 2 checks. Now we'll use 3 pi on 2. So I can just go and insert the 3 in there in that last equation. And it works. I get 0 as the answer. So that angle checks. I'm going to check both pi on 3 and 5 pi on 3. I'm going to check 5 pi on 3 first by going back and editing the last one we did. So there's 5 pi on 3 in there, and that one works. And now we'll go back and check pi on 3 just by eliminating the 5 from the last equation. And it works. So you can always check the answers that you get. Now, it's possible that maybe you miss some answers. That's a possibility. But you should never get the answers that you stated wrong because you can always check them like I just showed you. And the other option you can have as well to make sure you got all 4 answers is to put this equation in your graphing calculator and graph it. Cosine of 2x plus 1 minus the cosine of x. We want to know where that equals 0. So we'd be looking for the x-intercepts. We're in the radian mode, so our windows need to reflect that. Our answers are only going to be between 0 and 2 pi here. So I might choose my x minimum, though, to be something a little less than 0, just so I can clearly see the y-axis. So maybe I'll let my x min be negative pi on 6. So at least this way I'll see the y-axis. And my x max, I'll put it in as 2 pi for now. And I'll set my scale at pi over 2. I'm going to go from negative 5 to positive 5 on the y-axis. So now when I hit graph, I should only see 4 points of intersection because I found 4 answers. And I do. And you can check them. You can go into the trace mode and you can let x equal pi on 2. That was our first answer. And that works. Y does equal 0 there. You can go 3 pi on 2. That works. Y does equal 0 there. We can go pi on 3. That works. Y equals 0 and 5 pi on 3. works. You should never get these wrong. You can use your graphing calculator to check your answers every single time. Okay? But we had to use the substitution for cos 2x to get an equation that we could factor. And the only one we could use is 2 cos squared x minus 1, because the other two involve either just sine x or sine x and cos x as separate terms, so you can't factor. All right, question B then. You've got 1 minus cos squared x on the left equals 3 sine x minus 2 on the right. Remember from the Pythagorean theorem that 1 minus cos squared x is equal to sine squared x. So that's where we're going to start. We're going to make that substitution. Because we have a term of sine x on the right, I'm going to replace the 1 minus cos squared x with sine squared x. And then I'll bring the 3 sine x over to the left by subtracting it from both sides. And I'll add 2 to both sides. I have everything on one side equals 0 on the right, and I can factor this. The factors here will be sine x minus 1, sine x minus 2. So our solutions will come when each factor equals 0. Whoops. So our solutions will come where sine x equals 1 and 2. We can look on the unit circle and see where the sine of x equals 1. Remember, sine is the y value, and it equals positive 1 only in one spot between 0 and 2 pi, and that's at pi on 2 radians. Nowhere on the unit circle does the sine of x equal 2. So what do we do for that? Anyone remember? Why is it undefined? Hey, right. Remember the graph of sine only goes up to 1 and down to negative 1. There are no solutions for that because the graph of sine, you remember from chapter 5, goes up to 1 and down as low as negative 1. It never gets to positive 2. So that is the only solution, pi on 2. There are no solutions for where the sine of x equals positive 2. Now, just because it's not a value on the unit circle doesn't mean there's no answer. You could have the sine of x equals some decimal, any decimal, between negative 1 and positive 1, and you can get the answers. That's where we use that cast rule again. And we'll see examples of that. But it never equals 2 because the graph only goes up to 1 and down to negative 1. So in this case, we have only one answer that we need to check in the original equation. So it's 1 minus, and we have to do the cosine of pi on 2 all squared. So I need brackets for this. So there's the cosine of pi on 2, close the bracket so I can square it. So that's the only thing we have on the left side of the original equation, and you can see you get a value of 1 on the left. You should get the same value on the right when you let x equal pi on 2. 3 times the sine of pi on 2 minus 2 also equals 1. So the answer that we got checked. And again, we can use our graphing calculator. In this case, we put two equations in. Y1 would be the left side. 1 minus in bracket the cosine of x all squared. The left side goes into y1. The right side goes into y2, which is 3 sine x minus 2. When we graph these, we should see only one point of intersection. Right? We have two different sides of the equation, two different equations. Where are they equal? They're equal where they intersect. There should only be one, and it should be at pi on 2. So if I go into trace, and I let x equal pi on 2, there's our point of intersection. The graphs tell us that there's only one point of intersection between 0 and 2 pi, so that confirms that we only have one answer. We did check the one answer that we got, but this tells us that we didn't miss any. There are no more answers. So in this case, we have the same domain between 0 and 2 pi, which tells us where answers have to be in radians. It also tells us that 0 could be an answer, but 2 pi could not. For sine 2x, there's only one option, and that is 2 sine x cos x. There's only one option for sine 2x. And our next step is that we would factor. There's a common factor of cosine x. If you divide each term by cosine x, that's what we get. So our solutions will be where cosine of x equals 0, and where 2 sine x minus 1 equals 0. Which is where the sine of x equals 1/2. So on the unit circle, we want to see where the cosine of x equals 0. And again, cosine is the x value. We've already seen that that is 0 at pi on 2 and down at 3 pi on 2. And also where the sine of x equals 1/2. Remember, sine is the y value now, and that equals positive 1/2 here at pi on 6, and over here at 5 pi on 6. So there's our solutions that we got. So we could check those 4 answers in the original equation, or we could graph the original equation and check the 4 answers that way. I think that's the way I'll do it, because not only will it confirm our 4 answers, it'll also tell us if we missed any. So in this case, sine 2x minus cos x has to equal 0. Which means we're looking for the x-intercepts of that equation. So we look there, there's only 4 x-intercepts, so we didn't miss any answers. So just to check to make sure they all give us x-intercepts, the first answer we got was pi on 2. Y does equal 0 there, so it confirms that. 3 pi on 2. Y does equal 0, so that confirms that x-intercept. Pi on 6, and 5 pi on 6. You should never get these wrong, because you can always check. Right? Question B. You've got a cosine x term there, and you've got a sine squared x. But 1 minus sine squared x from the Pythagorean identity equals cos squared x. So we would have 2 cos x plus cos squared x equals 3, or if I make it all equal to 0, which is a step we need to do before we factor, and also rearrange the terms in order of descending power, that is the quadratic that we now want to factor. So the last 2 terms must multiply to get -3, and when I multiply out the outer and inner and simplify, I should get a positive 2 cos x in the middle, so a plus 3 and a minus 1 will give us that. In And you could have the -1 in the first bracket, the +3 in the second. It doesn't matter. So again, our solutions come where each factor equals 0. And so we get two potential set of answers coming from where cos of x equals -3 and cos of x equals +1. But there will not be any answers for the cosine of x equal -3 because the graph of cosine only goes up to 1 and down to -1. It never gets to -3. So there will be no solutions for that part. Only where the cosine of x equals 1. Remember, cosine is the x value. The only place it equals 1 is right here at 0 and 2 pi, but our domain tells us we can't use 2 pi. We can only use 0 radians. And if you just leave it at 0 without any unit, that means radians. We can write rads on it or after if we want. And we can use our graphing calculator to check. There should only be one solution here. So in this case, I think I'll make it one equation equal to 0 by bringing the 3 over. So I have 2 times the cosine of x plus 1 minus sine squared x, which is the sine of x all squared. And then if I subtract the 3 from both sides to bring it over, now I'm looking for the x-intercept. It should only be 1, and that's at 0. There's also one over here at 2 pi, but remember we can't use that because the domain tells us that x is greater than or equal to 0 and only less than 2 pi. So if we let x equal 0, y does equal 0. So that confirms our solution. So again, make sure you never get these wrong. You can use your graphing calculator to check your answers and also make sure you didn't miss any. So in this case here, now we're going to give our answers in degrees. 0 could be an answer, but not 360 degrees because x is only less than 360, not equal to. What I would do here is I would substitute the cotan for cos over sine. That's where I would start. And that's multiplied by sine x or sine x over 1. And because they're multiplied, we can divide top and bottom by sine x, they cancel. And so we're left with cos squared x equals cosine x. And if we make it equal to 0, because we have a quadratic here that we're probably going to have to factor, we do that by subtracting cosine of x from both sides. And we can take out a common factor of cosine x. So our solutions come where each factor equals 0. And so now we can look on our unit circle. Where is the cosine of x equal to 0? Well, that's at 90 degrees and 270. Remember, our answers have to be in degrees in this case. And where does the cosine of x equal 1? Only here at 0 degrees. We cannot use 360. So when we're checking this, our calculator has to change to degrees instead of radians. So we need to change our mode and we need to change our windows. Our mode will now be in degrees. And our windows will also be in degrees. So let's go from negative, let's say 90 degrees up to 360 degrees. And we'll set our scale to every 90 degrees. I'm going to put the original equation in there. So the left side, I'll put in y1 will be the cosine of x all squared. And on the right side, to do this right, I'll use the original equation, which is cotan x times sine x. I don't have a cotan button on the calculator, but cotan I can write as 1 divided by tan x. So I kept that together times sine x. So there should only be actually 3 points of intersection here. So second function trace, number 5 for intersect, enter, enter. I'll put my first guess at 0, and it is a point of intersection, so that confirms that answer. Second function trace, number 5 for intersect, enter, enter. I'll put my guess at 90, confirms that point of intersection. And the last one is 270. So I can just type in 270 if I want. That's a non-permissive value. And that comes from the fact that cotan can be written as either 1 over tan, so the tan x can't equal 0. We also wrote it as cos over sine, and that would say only sine can't equal 0. But that doesn't give you all the non-permissive values. You have to think of cotan in terms of 1 over tan. So tan can't be 0 or undefined, which means sine nor cos can equal 0. So that answer of 0 degrees doesn't actually work. It's a non-permissive value. So again, the graphing calculator showed us that. Because when I tried to find that as a point of intersection, I'm sorry, that wasn't 0, it was 270, I apologize. It wasn't 0, it was 270 that we just checked. Because at 270, there is no y value returned from that first equation. It's a non-permissive value. So again, the graphing calculator is quite useful, not only in checking solution, but in this case, showing that one of the answers we got was non-permissive. Yeah? But it worked for the graph. Oh, and you know why? If we look at, because we did 1 over tan. So had we written it as cos over sine, then I think that would have returned. So if we did cos x divided by sine x times sine x, and now we graph it, and we go into the trace. So that's on the cos squared x, but when we go on the other one, you're absolutely right. There is no y value returned. And if we check 90 degrees, that was the other one we got. Yep. It works for that one. Let me just look at this again, make sure I wrote that in there right. I don't think I did. I think I need to put brackets around that to keep it together. So I'm going to insert a bracket there, and then also at the very end. Oh, that's not right. I put it in the wrong spot. it should have been after the sine x and before the cos x. So now when I check 90 degrees, so right now I'm on the equation cos squared x, so that's why I get an answer returned. But when I go to the other one, I let x equal 90. No, it works. Looks like 90 is going to work. But 0 doesn't. So it looks like we only get one answer here. Because it's where sine x equals 0. But if I put the equation as 1 over 10, didn't we already have that in there? And we checked and 90 didn't work, didn't it? Let's go back and check. I've already crossed that one off. Now we're just checking to see if 90 works. So instead of having cos x divided by sine x there, what if I wrote it as 1 over tan x for cotan? And that's times sine x. So now when I graph, I go into the trace mode on that second one, and now I let x equal 90. It doesn't work. So yeah, it turns out there are no solutions to this one. So again, graphing calculator comes in quite handy. There are no solutions to that one because all the answers we got are actually non-permissive. 30 is fine. Right. There are no zeros at 30 degrees. So we want to solve this one now. Again, make sure you look at the domain. It's between 0 degrees and 360 degrees. 0 is included, but 360 is not. So I've got a sine squared x on the left side equal 1/2 tan x cosine x. So what I would do here is I would change the tan x to sine x over cos x. And that's multiplied by cos x or cos x over 1. I can divide top and bottom by cosine x. And they cancel, so all I have left on the right side is 1/2 sine x. If I subtract it from both sides and make it equal to 0, I can factor out a common factor of sine x. And so our solutions will come here where each factor equals 0. And for that second one, that's where the sine of x equals positive 1/2. Note we do have a denominator of cosine x here, so none of our answers can be where cosine of x equals 0. But I don't think that's going to be an issue here because our answers will come where actually sine x equals 0, which is where cosine of x will equal either 1 or negative 1, as well as where sine x equals 1/2. And there's no zeros involved there. So first, where the sine, the y value is 0, is there. And remember, over here as well as back at 360, but we can't use that because our domain tells us that. So our first two answers are 0 degrees and 180 degrees. Our second set of answers will come where the sine of x equals positive 1/2. And again, sine is the y value, equals positive 1/2 here at 30 degrees and over here at 150. So there's our 4 answers. which again, we can check that in our calculator. So the left side will be sine squared x, or the sine of x all squared. The right side would be 1/2, or 0.5, times the tan of x times the cosine of x. So we should see 4 points of intersection here. And they would correspond to those 4 answers. So second function trace, number 5 for intersect, enter, enter. We'll put our first guess at 0, and yes, that works. We'll check the other ones as well. (30° works. 150 works. And 180 works. The only other point of intersection looks like it's at 360°, but we can't state that because our domain tells us we can't go and include 360. Okay. So now we're going to solve this one, and it says give the general solutions in radians. So remember, the general solutions include all solutions from negative infinity to positive infinity. So that's where we use multiples of the period. And we always use multiples of something involving n, where n is an element of integers. But first we have to solve the equation. Sine 2x is 2 sine x cos x. And I'll bring over the root 2 cos x to the left side by subtracting it and making that equal to 0. And there is a common factor of cosine x here that we can take out. So our solutions again will occur when each factor equals 0. So this will be where 2 sine of x equals root 2, and where the sine of x equals root 2 over 2. Which is on the unit circle. Now, we want to give the general solutions in radians. So first, where is the cosine, which is the x value, equal to 0? And that is up here at pi on 2, and down there at 3 pi on 2. These two angles are exactly pi radians apart no matter which direction we go, so we can express them as one statement, starting at pi on 2 and then every multiple of pi after that. Whether we go clockwise or counterclockwise, it doesn't matter. We end up at the same spot. So pi on 2 plus n pi will be our first set of general solutions. And then our second set of answers come where the sine, which is the y value, equals positive root 2 over 2, which is here at pi on 4 and over here at 3 pi on 4. Now, these two angles are not the same distance apart whether you go counterclockwise or clockwise. It's much further around going clockwise than it is counterclockwise. So because of that, we have to write two separate statements, one involving pi on 4, the other involving 3 pi on 4. So it'll be pi on 4 plus 2 pi n. We have to go all the way around the circle to get back there, as well as 3 pi on 4 plus 2 pi n, where n is an element of integers. So there's where our solutions will come from. There are no denominators anywhere in that equation, so there are not any non-permissive values to worry about. Those are the general solutions. So same thing with this one. Cos 2x on one side equaling cos x on the other. Once again, we have three options for cos 2x, but I would use the one that only involves cosine, which is 2 cos squared x minus 1. And if I bring the cos x over and make it equal to 0, and then I'll rearrange the terms, and then factor. So you need the minus 1 with the cosine x, the positive 1 with the 2 cosine x. So when you multiply these out, the outer products will be negative 2 cos x plus 1 cos x gives us the minus 1 cos x in the middle. And again, our solutions come where each factor equals 0. So we want to know where the cosine of x equals negative a half as well as positive 1. The cosine of x equals negative a half. Over here, and we want to be in radians, so 2 pi on 3, and down here at 4 pi on 3. Again, these two angles are not the same distance apart depending which way you go, clockwise or counterclockwise, so we're going to have to state both. 2 pi on 3 and 4 pi on 3 both plus 2 pi n. And then we also have where the cosine equals positive 1, which is right there. And that's the only place. So that's every multiple of 2 pi. So we'll also add 2 pi n there. That shows every multiple of 2 pi, where n is an element of integers. Okay? So this next one, we involve a reciprocal ratio because we have 3 cosecant x, and cosecant is 1 over sine. So that's what I'm going to start with. I've got 3 over 1 times 1 over sine x. So if I multiply that rational expression, top times top, over bottom times bottom, we see that 3 cosecant x can be written as 3 over sine x, because cosecant is 1 over sine. So my next step would be to multiply all 3 terms by sine x. That gets rid of the denominator of sine x on the right side. Those sine x's cancel. So you have 2 sine squared x equals 7 sine x minus 3. Because we have a sine squared x and a sine x, we're going to have to factor, so we want to make it equal to 0. And now we'll factor. So these numbers are both going to have to be negative. We'll have to put the -3 there. So the outer products will be -6 sine x. The -1 must go there. So the inner products will be -1 sine x. -6 minus 1 gives you the -7 in the middle. And again, our answers will come when each factor equals 0. And you remember the graph of sine only goes up to 1 and down to -1, so there won't be any solutions for that second one. Only where the sine of x equals a half. And again, we want to give our general solutions in radians. Where does the sine of x equal +1/2? So that's there at pi on 6, and over here at 5 pi on 6. Again, it's not the same distance to go from one of these angles to the next, depending on whether you go counterclockwise or clockwise. So we have to have two different statements. One for the pi on 6, one for the 5 pi on 6. Right, so for this one, on the right side, 5 times secant x. Well, secant is 1 over cos. So that'll be 5 over 1 times 1 over cos, just like we did the last one. That right side we can write as 5 over cosine x. And then we would multiply everything by cosine x to get rid of the denominator of cosine x on the right. They will cancel. And so there's the quadratic that we now need to solve. So we'll factor. So the last terms have to multiply to get -5, and when we multiply this out, we have to get a +2 cos x, which will only work if I put a +5 there and a -1 there. You see the inner products will be 5 cos x, the outer products will be -3 cos x. 5 cos x, take away 3 cos x, leaves us with 2 cos x in the middle. So our solutions will come where each factor equals 0. And this will be where the cosine of x equals -5/3 and +1. 5/3 is greater, actually -5/3 is less than -1. Again, the graph of cosine only goes up to 1 and down to -1, so there are no solutions to that. Our only solutions will come where the cosine of x equals 1, and that is at 0, at pi, back to 2 pi, or essentially every multiple of pi. Doesn't matter whether you go counterclockwise or clockwise, these angles are the same distance away. So we can write one statement every multiple of pi. So x would equal n pi, where n is an element of integers. Huh? Oh, yes, I'm sorry. Thank you. Over here, it's -1. Yes, thank you very much. So we'll say 2 pi n. 2 pi n. Okay? that's it. Yep. So questions 1 on 2 on page 320 you should work on for practice. I will post the solution to Google Classroom, so you're not going to hand this in, but I would really encourage you to do it for the practice. So again, on Tuesday, we're going to have a quiz, and our test won't be Thursday because I want to make sure that you guys have the opportunity to go through the quiz. Okay, so the quiz will be Tuesday. On Thursday, we'll go through the quiz. You'll have more time to work on the review, and then our test will be the following Monday. Actually, Friday there is no class, so it'll be the following Tuesday. Friday's a PD day for us. Okay? So, but you do have a quiz on Tuesday. And I will get the review assignment and handout